Section 1.2, Applications of Linear Equations and Rational Equations. First page reads, we find algebraic applications in all sorts of subjects, including economics, physics, medicine, and countless other disciplines. In this section, we learn how to solve a variety of useful applications that involve linear equations and rational equations. Before we look at some specific examples, it is important to first practice translating or converting verbal statements into mathematical statements. So, when solving word problems, it is important to recognize keywords and phrases that translate into algebraic expressions involving addition, subtraction, multiplication, and division. So we're going to do these 5 real quick. I think we got a lot of examples today. We'll do current page. All right, so follow along. Today might be pretty quick because there's a lot of stuff that I need to cover and not much time to do it. So I'm going to go ahead and just breeze through these pretty quickly. So rewrite each statement as an algebraic expression or equation. So A reads 7 more than 3 times a number. Okay, so we think about it. So 7 more. So we're adding 7 to something, right? 7 more than 3 times a number. It doesn't really matter what we call the number. We can call it n, we can call it x. That's it. This is the equivalent of that statement, A. 7 more than 3 times a number. B. 5 less than twice a number. So 5 less. All right, well that must, we'll go ahead and put the 5 less there, right? So 5 less than twice a number. So doesn't matter what variable we use. In A, we used n for number, but for B, we're going to just go ahead and use x. So we said twice a number. Okay. So that is indeed 5 less than twice a number. C, 3 times the quotient of a number and 11. Okay, so this we're getting a little bit more complex. We're using the word quotient there. So 3 times the quotient of a number and 11. Okay, so if it's 3 times something, so we're just going to put the 3 there, right? 3 times, and put a big dot there. 3 times the quotient of a number and 11. So quotient means division, so it's the quotient of some number and 11. So what does that mean? So that means we're going to put, we're going to use n again for sort of some number and 11. Okay. Or equivalently rather, we can say 3n over 11. D, the sum of a number and 9 is 1 less than half the number. Okay, so now we're getting a little more complex, and the complexity here would be this. The is, okay? So the is, when we talk about mathematical statements, that's equivalent to saying equal to, okay? So we're going to translate that essentially into an equal sign. So we're going to say the sum of a number and 9. Okay, well that's pretty easy, right? The sum of a number and 9, so we'll go back to using x for this one. All right, everybody agree that that is the sum of a number and 9, so sum being addition. And then we have that is in there, so we're going to go ahead and put that equal sign. Is 1 less than half of the number. So if we did the 1 less than, so that's going to be, 1 less than half of that number. So half the number would just simply be 1/2 x. And that is the sum of a number, again, the left side, is, and then that's the equal sign, 1 less than half that number. So E. Okay. So the product of a number and 4 is, so we're going to go ahead and have that equal sign there again, right? So the product of a number and 4, well, that seems pretty easy, right? A number and 4, we'll go back to using n. All right, that would be that's the product being multiplication. The product of a number and 4 is 1 more. Okay, so we're going to have a plus 1 out here. 1 more than 8 times the difference of 10 in the number. Okay, so let's zoom in on this. 8 times the difference of 10 and the number. So 8 times something, so we're going to have an 8 out there. Okay, and it's going to be the difference of 10 and the number. So this tells me that we're going to be having that, essentially in a parentheses, right? It's going to be 8 times something, and that something would be the difference of 10 and the number. The difference being a subtraction sign, so 10 minus n. Let's see if I can erase that a little bit. The difference of 10, and we're going to stay consistent, use the n since we use it there, and we said it was 1 more, so plus 1. Okay, so that's a very just quick breakdown of translating mathematical statements into equations. All right, so over in our examples over here, we went from using words, and over in nice colorful, that is pretty colorful, you gotta admit, right? And the colorful solutions, rather, I just translated those words into algebraic equations, and that's very important because that's what we're going to be doing today, which is really nice because here we are on section 2, and I'm already answering the question of when are we ever going to use this. Okay, so that's that. These are our solutions. All right, you know what? Let's look at here. Okay, because I'm gonna be honest with you, I've never heard of George Polya. Not that he's not famous or anything, right? But apparently he was this genius that came up with some 4-step plan. Right, so it's important to have a strategy in place before trying to solve an applied problem. George Polya, a Hungarian mathematician who taught at Stanford for many years, was famous for his book How to Solve It, and I actually have that book. That's kind of funny. I didn't know it was him. It's got to be a different book. The mathematics lab at the University of Idaho was named the Polya Mathematics Learning Center in honor of him. So this problem-solving model can be broken down into 4 steps. And these are the 4 steps. And if I recall, we break it down even more. Yeah, here we go. Now the thing is, you can follow this 4-step guide, and there's nothing wrong with it, right? Everybody likes algorithms, but understanding the problem, step 1, read the problem several times, and that's very important. Read the problem several times until you have an understanding of what's being asked. And today we're going to be going over quite a few of them, and I'm going to try and break down, my thought process when I see them. If possible, create a diagram. It's also very important. Charts or tables to assist you in your understanding. Step 2, pick a variable that describes the unknown quantity. So obviously, in the first examples, I was switching between x's and n's for the numbers. But we'll see here in a moment why sometimes you might want to use like an H for hot dog, or I think we're using. I think one problem's coming up as touchdown, so we might be using a T for touchdowns or something. Okay. All other quantities must be written in terms of that variable. So if we're using if we are making a mathematical statement, equation, and we're going to use H for hot dogs, the rest of the problem also probably needs to be in hot dogs, because if we're trying to solve a linear equation in one variable, that's the way to do it. If we have a linear equation and 2 or 3 variables, well, then you need 2 or 3 equations to solve that system of equations. Step 3, carefully solve. Step 4, make sure you have answered the question, then check all answers to make sure if they make sense. Okay, so as promised, we got touchdowns. Actually, let's see. Now, what we're gonna do, I'm just gonna snip this and discuss it, because this is one of the easier ones, and there are. So, oh no, I think I froze it. All right, so it's gonna crash, and I'll have to come back and do it again. This is where it did this to me yesterday, and I think it did this to our class last week as well. So I just need to, if I'm snipping, I need to commit to it. Maybe not. Oh, maybe not. Oh, that's good. Okay, so let's snip this whole thing and I will discuss it. Snippet better. Yeah, the rest is just solving. Okay, so going through this, all right, the problem reads, Roger Staubach and Terry Bradshaw, these are both quarterbacks in the 70s, were both quarterbacks in National Football League. Ah, there it is. In 1973, Staubach threw 3 touchdown passes, more than twice the number of touchdown passes thrown by Bradshaw. So let's see if we can highlight this. If the total number of touchdown passes between Staubach and Bradshaw was 33, how many touchdown passes did each player throw? So what we're going to do is we would break this down, and we would say, okay, so apparently we don't use touchdowns, or T for touchdowns. But, you know, if we were to think about this intuitively, this is asking if the number of touchdown passes between Staubach and Bradshaw was 33, how many touchdown passes did each player throw? So 33. Okay, so we're thinking, you know, Staubach threw some amount, Bradshaw threw some amount, and their total is 33. Right, and then earlier I had said, whenever you solve these equations, you want to narrow it down into one variable. Obviously, S and B, that's 2 variables, okay? But that's why the highlighted section up there, Staubach threw 3 touchdown passes more than twice the number of touchdown passes thrown by Bradshaw. So similar to our examples in the first example, you know, it's 3 touchdown passes more than 3 touchdown passes more than twice the number of Bradshaw, and that's where we'd get this 2b plus 3. Okay, so Staubach, and maybe I should keep in the order of this. So we did Bradshaw plus Staubach. Okay, all right. So Bradshaw, how many touchdown passes did Bradshaw throw? Well, Bradshaw threw Bradshaw amount of touchdowns. Okay, Staubach, however, he threw twice the amount of Bradshaw, but 3 more than twice, and their total is 33, and that's the equation that we'd set up. And at this point, hopefully, you would be able to solve it at this point. Obviously, you know where to go to look for the answers. This will be another one where I'm just going to snip it. Now, don't think that I'm taking the lazy way out here, because you'll see here in a moment when I do actually get into the nitty-gritty that I will be doing. There'll be plenty of work for me to do and to show you how to solve these. But these, in my opinion, are fairly simple, pretty easy to explain, but just reading it. All right, the other ones here in a moment, not so much, and you'll definitely get your money's worth. So example 3, one number is 3 times another number. Determine the 2 numbers if the sum of their reciprocals is 4. Okay, so if we just read this, then it says one number is 3 times another number. So in this particular example, we're just going to use the number n. Okay, well, one number is 3 times that number. Okay, 3 times that number. All right, now, and then it goes on to say, determine the 2 numbers if the sum of their reciprocals. All right, and then we just talk about the reciprocals. Well, that's just 1 over n, and it says the sum. Well, it's just 1 over 3n is 4. And then, of course, we solve from here. We do, we multiply by the least common denominator, which would be 3n, and proceed. Okay, so example 4. Now, this is one that I will do. Before we proceed, let's see what it says. It reads, in this objective, we use some common formulas from geometry. You may want to review the formulas and refer to them while working through the following examples. Okay, so your geometry examples, they're just some things you have to memorize, know, the area of a triangle, the area of a square, things like that. And this particular case, we're going to be talking about looks like the perimeter. And so we're going to have to, and I'm going to go ahead and, no, I'll just draw that. So we're going to think our way through this problem. Pretty simple, pretty straightforward rather. I don't have a square drawing tool, do I? No, we'll just deal with it. We're talking about a college basketball court. So the length of a college basketball court is 6 feet less than twice its width. Okay, so the length would be these sides, right? And the widths would be these sides, correct? Okay, so it's saying that the length of a college basketball court is 6 feet less than twice the width. Okay, so we have our length here, and it is 6 feet less than twice the width. So we're going to say twice the width, but it's 6 feet less, right? Okay, well, what's the width? Well, it doesn't tell us. Therefore, I mean, it's the width is the width, right? And then saying if the perimeter is 288 feet, what are the dimensions of the court? So we have the perimeter being 280, and I probably shouldn't have put it in the middle because that kind of looks like an area, but we understand context, right? So the perimeter is 288 feet. Okay, so how do we go about solving this? All right, so it looks like we need to solve for W, right? Because that's what we don't know. So let's think about this intuitively. The perimeter here. If the perimeter is 288 feet, that's saying all around this rectangle is 288 feet. Okay, so let's imagine, just let's draw another square, a better square. No, we don't need another square. What's wrong with me? The perimeter of any square, okay, it looks like it's going to be the length, and then this would be the length, right? So it's going to be length plus length, and that's going to be the width and the width, right? Or some W there. So it's going to be plus width, okay? Or in other words, we can say the perimeter is 2 times the length plus 2 times the width, right? Okay, well, we have the information we need, and we have the length in terms of width. So we would say that the perimeter, and we have a number for the perimeter, right? The perimeter is 288 feet, and that's equal to 2 times, well, what's the length? Well, the length is simply 2W minus 6. And let's put that in red. No, we'll do this. Never mind, sorry. 2W minus 6, and then plus twice the width. And then we solve. We just solve for W. And then once we solve for W, we can figure out what the width is. And then whenever we get the width, we can just plug that in for the W here, and then we'd get the length. Okay. Okay, so this one, we're going to snip this one as well. Let me snip the whole thing. We'll just do it here. Okay, so this is another one of those examples where you just kind of need to know your geometry. Now, at the same time, I know on the test you'll be given, if you have a trapezoid, for instance, I'm pretty sure it's just a triangle though. You'll be given what the formula is, as opposed to this one, because to be honest, if you woke me up this morning and say, "Hey, Sherman, what is the area of a trapezoid?" I definitely wouldn't say, "Oh, it's half height times A plus B," where A and B are the bottom and top, right? So you'll be given that. But let's go ahead and read this and think our way through it. I'm pretty sure example 6, it was where I started actually doing problems. So again, I'm not being lazy here, just trying to be quick because there is a lot of stuff I need to go over. So example 5, determine the side lengths of a trapezoid. Suppose that the area of a trapezoid can be represented by the expression 6 over x square feet. Okay, so that's the area. And suppose that the lengths of the parallel bases of trapezoids can be represented by the expressions 2 over x feet and 3 over x plus 1 feet, respectively. If the height is 4 feet, determine the value of x. Okay, so what we need to do here is we need to recall, and again, you'll probably be given these formulas. Recall that the area of a trapezoid is half the height times a plus b, where a and b are the parallel bases. And from here, all you simply really have to do is just substitute, right? The area, 6 minus x, well, that's given to us. Okay. The height, well, that's given to us. And then the parallel bases, a and b, well, that is given to us. Right? And then we just solve for x. So you see why I did more or less hand wave through that. But let's get to some nitty gritty. All right, so in example 2, the equation turned out to be a linear equation involving integer coefficients. In the next two examples, we see that the equation turns out to be linear equations involving decimals. You may want to review the techniques used to solve linear equations involving decimals, which we did last week, and of course you can find them on YouTube. Which, by the way, I used to record my lectures when I worked in Florida, and at least I don't think I really paid attention, but I went and looked at the metrics on YouTube, and it's really crazy how much information I have at my fingertips to see who all's watching what and for how long. And it's pretty crazy because let's say, we have an hour-long video, it shows the average viewers at each time. And then by the 50-minute mark, there's like 2 students left that have actually watched that far. Nothing on you, just saying. Okay, so we've got a good problem here. Billy has $16.50 in his piggy bank consisting of nickels, dimes, and quarters. Billy notices that he has 20 fewer quarters than dimes. If the number of nickels is equal to the number of quarters and dimes combined, how many of each coin does Billy have? Okay, so this one looks like it's a little bit daunting. All right, but first let's just break this down into what is being asked here. Okay, so Billy has $16.50 in his piggy bank, and for the sake of just kind of being consistent, I'm just gonna put $16.50 over here, but I'm probably gonna end up moving it. So yeah, I'm gonna end up moving it. Consisting of nickels, dimes, and quarters. Well, that's not hard, right? So nickels, plus dimes, plus quarters, and that's why I should not have shot it way over there, is equal to $16.50. Does that make sense? So the number of nickels, the number of dimes, and the number of quarters is equal to $16.50. But that's not necessarily all of it, right? Because if I just found out the number of nickels, let's just say is, for the sake of this, is just like 10, right? And then dimes, whatever. We'll say dimes are 20 and quarters are 30. Okay, well, that's 60. Right? That doesn't make sense if I said 60 is equal to $16.50, right? The number of nickels, the number of dimes, the number of quarters, they have a value, correct? It's not just the number of them. So what I'm going to have to do is I'm going to have to think of another way to interpret this. And that's just a pretty easy step from here is giving them their actual monetary value, which would be 0.5 N plus 0.1 D plus 0.25 Q is equal to $16.50. Okay, so now I've given them monetary value, right? But obviously, as I mentioned before, well, we need to have this broken down into one variable because this is 3 variables: an N, a D, and a Q, right? That doesn't help me out at all. So now I got to continue reading on through the problem. Okay, so this reads, Billy notices that he has 20 fewer quarters than dimes. Okay, so what I'm going to have to do is I'm going to have to, and I'll put this out here. We'll do nickels, dimes, quarters. Okay, sorry. Billy notices that he has 20 fewer quarters than dimes. Okay, so how do I figure out what that's trying to say? So it's saying he's got 20 fewer quarters than dimes. So what we're going to do is we're going to put this in terms of dimes. Okay, so in quarters, he's got dime amount, right, but it said 20 fewer. So that's going to be my Q variable, D minus 20. It goes on to read, if the number of nickels is equal to the number of quarters and dimes, okay, so the number of nickels is the same as quarters and dimes. So how many dimes do we have? Well, it doesn't necessarily tell us. So we're going to say we have D amount of dimes. Similar to Bradshaw's touchdowns, we had Bradshaw amount of touchdowns. Well, we have D amount of dimes. Okay, it's number of nickels equal to the number of quarters and dimes combined. So we combine them, so it would be the sum of it, right? So it would be dimes plus by number of quarters, which was D minus 20. And then, of course, my dimes, well, that's a dime amount. Okay, hopefully you can see this all coming about. So now I have my variable n, which would go here for n, my variable dime, which honestly, I mean, nothing changes there, does it? I guess I can keep that there. And then my variable q, quarters, goes here. So I can rewrite this now into something that looks like this. Let's see if I can, now we'll do this. 0.5, okay, the amount of nickels I've got. And that is going to be, I'm substituting in n for n here. Okay, again, n here for n here would be dimes plus dimes minus 20, which was the number of number of quarters I had, right? Plus 0.1 D, because that's the amount of dimes. My quarters, maybe I should have, we'll see. And then my quarters was 0.25. No, I didn't need to change. All right, so I'm gonna rewrite this and make it a lot prettier. Sorry. I want to make these notes nice and neat for you. How? Okay. So let's do this again. So we've got my nickels. Maybe I should put it. We'll have a little divider. Is that better? Maybe. I don't know. We'll see. So let's try again. So 0.5 times n, and we said n was D plus D minus 20 plus 0.1 dimes plus 0.25 times Q, which was D minus 20, and that's equal to 1650. Okay, it's not the neatest thing I've ever done, but that's it. Okay, and this is a very not good bracket, so let's fix that up a little bit. And then we solve this problem for D. And then once we figure out the number of dimes we have, we can then figure out the number of nickels and the number of quarters. And again, for these problems, for these application problems, it's the setting up of the problem that is the hard part. At this point, I'm hoping you can look at something like this and in time be able to solve it, because this is something that we did last week and something you've done since high school. So let's move on. Not to mention, excuse me, I'm showing you where you can find these problems, so you'll be able to go back and check your answer against the book. Okay, so something else. Let's think about this intuitively. Okay, so we've got a mixture application. How many millimeters of a 70% acid solution? Honestly, the picture, I should have snipped the picture, but for the sake of just me being a student as well, we'll just go at it this way. How many millimeters of a 70% acid solution must be mixed with 30 milliliters of a 40% acid solution to obtain a mixture that is 50% acid? Okay, so what we're going to do is we're going to just think about this. So we're going to do, probably does help to just draw a picture. So how many millimeters of 70% acid solution must be mixed with 30 millimeters of 40% acid solution to obtain a mixture that's 50% acid? So this is going to be easy. So not easy, but we're going to have something be 50% 50% acid solution. How many millimeters? 70%. So 70% and 40%. Okay, so some 70% plus 40%. And honestly, this I probably shouldn't go about this. Whatever. So it's saying how many millimeters of 70% acid solution must be mixed with 30 milliliters of 40% acid solution to obtain a mixture that is 50% acid solution. Now, obviously, this doesn't make sense, right? Because 70% plus 40% does not equal to 50%. But bear with me. We're going to be talking about we're going to put something underneath it when we talk about millimeters. So how many millimeters of a 70% acid solution? So, you know, we don't know. That is our unknown. Of a millimeter 70% acid must be mixed with 30 milliliters. Okay, so 30 milliliters. We're going to put a 30 here. And it goes on to say obtain a mixture that's 50% acid. Okay, so that 50% acid solution, how many milliliters are going to be in that 50% acid solution? Well, it's going to be x plus 30, right? And so let's think about this intuitively. If I have, I mean, it honestly is kind of self-explanatory, but let's say, how many gallons of milk do I need? If I'm adding 4 gallons to it, well, how many gallons do I have total? Well, I've got x plus 4 gallons. Okay, so that's all the blue is saying. So we have, how many of some amount of milliliters do I have of this mixture added to 30 milliliters? Okay, we'll combine, it'll be x plus 30. Okay, so now we can start making sense of things. So let's go down here a little bit, and we're going to say 70%. So whenever we talk about percentages in mathematics, okay, we don't write 70, do we? No, we write what? 0.7. So we're going to say 0.7 of that unknown amount, okay, plus 0.4 times 30, that amount of milliliters, and it's going to be equal to 50%, which is 0.5 of x plus, that's a terrible plus, 30. And we set up the problem. Okay. Now, obviously, again, in the red, it does not make sense by itself, but that is just a thought process, because again, 70 plus 40 does not equal to 50. But I'm trying to trying to put you through my thought process of what I'm doing, and I know that I need a certain amount of 70% solution, which can be seen here, a certain amount of 70% solution, plus what we have here, right? 30 milliliters of that 40% solution, and it's going to be equal to 50% of their solutions combined. Okay, so from there we solve and we can proceed. Okay, simple interest. Okay, so this reads that Kristen inherited $20,000 from her aunt Dawn Ann. Well, that's nice. With the stipulation that she invests part of the money in an account paying 4.5% simple interest, and the rest in an account paying 6% simple interest, locked in for 3 years. If at the end of 1 year total, at the end of 1 year, the total interest earned was $982, how much was invested at each rate? That's really good. So she gets almost a 5% return on her investment of investing $20,000. Thank you, Aunt Dawn Ann. So let's think about this. We're going to go backwards, because I actually don't like doing the equal sign way over here, because it just kind of messes up my flow. So we're going to do it this way. So if at the end of 1 year the total interest earned was $982.50, so total $982.50. So the way we set this up is we're going to say, okay, so she's going to invest some amount of money into an account paying 4.5%. Okay, so I'm just going to go ahead and skip the whole 4.5 part. And how much is 4.5% if I put it in decimal form? Okay, well, that's going to be 0.045. That's 4.5% written in decimal form. Okay. And then she's also going to invest. Oh, this is a good example. She's also going to invest, and the rest is in an account paying 6%. Okay, so the rest. How do I write the rest? Okay, so for now, we're just going to put R for the rest. Okay, we're going to put R for the rest, and that's going in there for 6%. So 0.06. Okay, so obviously this doesn't help us, does it? We've got two variables, but we're so close to figuring this out. If X is how much she invested into 4.5%, and it says the rest are an account paying 6%, how in the world do I write the rest? Okay, so let's think about it. Let's do some number games here. Okay, let's say that this X is $5,000. All right, and $20,000. Well, the rest, if somebody invests $5,000, would be $15,000, right? Okay, so if she invested $5,000, the rest would be $15,000. How else can we think about that? Okay, well, we could think about this is 20,000 minus this, minus 5,000, right? So what we're going to do is we can write this as 20,000 minus X. Does that make sense? Hopefully. So we're going to change R to 20,000 minus X. And then that was at 0.6%. 0.06, sorry. There. So now everything's filled out, right? Starting from the top, she inherited $20,000. Great. With the stipulation she invests part of the money in an account paying 4.5%. That's this part. And the rest in an account paying 6%. And this would be the rest. 20,000 minus what I invested in that first account, which was $5,000. Or wait, no, not 5,000. I don't actually know the answer. Without just my guess. It'd be weird if it was 5,000, huh? And then it says at the end of 1 year, the total interest earned is $982. How much was invested at each rate? And then, of course, we can figure that out doing algebra. So that's example 8. All right, so apparently the answer was 50. No, okay. Well, the 4.5% was 14,500, and the 6% was 5,500. But no big deal. Again, I was just guessing. Uniform motion. Okay, so let's read this. To solve, no, this is actually pretty good. We're gonna go and paste this. Probably should just cut all of it. Okay, so to solve uniform motion problems, we use the formula D equals RT, which is distance is equal to rate times time. Right. So using a table can often help to organize information, and we'll make a table for this one. Caution: when working with the formula D equals RT, the units for rate and time must be consistent, and we'll see that in this problem actually. For example, if the unit for rate is miles per hour, then the unit for time must be in hours. And we'll see that again. So, this is a pretty good problem. What time do we get out of here? College Algebra 210. Oh, we got plenty of time, I think. Rick left his house on his scooter at 9 a.m. to go fishing. He rode his scooter at an average rate of 10 miles per hour. At 9:15, his girlfriend Deb, who did not find Rick at home, pedaled after Rick on her new 10-speed bicycle at a rate of 15 miles per hour. Oh my god, I can tell right now there is eyeballs rolling in the back of your head. If Deb caught up with Rick at precisely the time they both reached a fishing hole, how far is it from Rick's house to the fishing hole? All right, so we're going to make a table. Hopefully, the process of reading that did not kill you. Rick and Deb. Okay, so we have our formula. This is going to be an application of uniform motion, and you can just kind of distance equals rate times time. That's something that you are going to be using, and I guess we quite a lot. And you need to be able to identify it whenever you see it. And it's really easy to tell because you're going to be having, distances in the problem, and we're going to have a rate and of course a time. Okay, so if we did, and looks like we'll do rate times time. So put that up here. Rate times time, that's equal to distance. And I don't necessarily need to put this here, but I guess I will to make it look nice and neat. And I'll do a different color. All right, so Rick, what is Rick's rate? Well, Rick's rate, it reads, is 10 miles per hour. 10 miles per hour. And actually, before I continue here, let's examine the distance equals rate times time. It's pretty easy. In my opinion, it's very intuitive. Okay, so distance equals rate times time. Okay, well, think about it. If your rate, let's say you are a speed demon and you are driving at 80 miles per hour. Okay, and you drive for 5 hours. Okay, well, what's your distance? Well, it's 80 times 5. That's 40. Or well, 8 times 5, sorry. 8 times 5 is 40. 80 times 5 would be 400. So your distance would be 400 miles. Okay, so distance equals rate times time should be very intuitive to you, whether you know it or not. All right. Now, so what is Deb's rate? Well, she is significantly quicker at 15 miles per hour. Okay, so we got the rates down. Now the time, okay? So this says that okay, so we're going to have to use time as our variable, it looks like. He rode his scooter at an average speed of 10 miles per hour. At 9:15, his girlfriend Deb pedaled after Rick on her new 10-speed bicycle at a rate of 15 miles per hour. If Deb caught up with Rick at precisely the time they both reached the fishing hole, how far is from Rick's house to the fishing hole? Okay, so it looks like Deb is the time we're going to be dealing with. Okay, so Deb, the time it takes her to reach the fishing hole is going to be t amount of time. There, t amount of time. Okay, so it's going to be very, very tempting here because it says right here at 9:15, his girlfriend Deb pedaled after Rick on her new bike. So it's going to be very tempting to say that Rick's time is time plus 15 minutes because he left at 9 o'clock, right? So if Deb's time is, t, it'd be very, 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 very tempting to say Rick's time would be t plus 15. But looking at this caution here, big deal. When working with the formula d equals rt, the units for rate and time must be consistent. For example, if the unit for rate is in miles per hour, then the unit for time must be in hours. So we're not going to put t plus 15 because 15 is minutes. If we're using 10 miles per hour, we need to put this in hours. And 15 minutes in hours is 1/4. Okay, and if distance is rate times time, well, that's just easy. We're just gonna make the the equation 10 times t plus 1/4. I think my arm touched over there. And then this is 15 t. Right, and here at the end of the problem, it reads, if Deb caught up with Rick at precisely the time they both reached the fishing hole, all right, precisely that time. So they will have went that same amount of distance. Well, not necessarily the same amount of distance for one another, but they met there at the same time. Their distances that they traveled are the distances that they traveled. I know that's not very what's the word, eloquent, but it's true. So that must mean that what we're going to have to do is we're going to have to equate their distances with one another. So in order to set this problem up, we would say 10t plus 1/4 is equal to 15t, and then we'd solve for t. Okay. Hopefully that helped you out. Making a table does help, especially when we know our formulas. Again, distance equals rate times time. How did I know to equate this? Again, it reads, Deb caught up with Rick at precisely the time they reached the fishing hole. Okay. So that would be that. Except 10. So this one, it's very similar to the previous problem, but we'll snip the whole thing again, and we'll go over it together. Okay, so the problem reads, an airplane that can maintain an average velocity of 320 miles per hour in still air, okay, where there's no headwind or tailwind, is transporting smoke jumpers to a forest fire. On takeoff from the airport, it encounters a headwind and takes 34 minutes to reach a jump site. The return trip from the jump site takes 30 minutes. What is the speed of the wind, and how far is it from the airport to the fire? Okay, so in order to get to this, we need to look at what's being asked here. And once again, we're going to be putting our attention down here. Distance is equal to rate times time. Okay, so this is saying that an airplane can maintain an average velocity of 320 miles per hour. So right away, we can say their rate is 320 miles per hour, right? Okay, and we have it broken up into headwind and tailwind. With going against the headwind, okay, that's going to impede us a little bit, okay? We don't know how much, but we know it's going to impede us. It's going to impede us whatever the speed of the wind is, which we're going to call W, okay? Well, on the return trip, we have the tailwind, so we have the wind behind us and it's pushing us, so it's going to help us out, and so we're going to have a faster rate. Okay, so that would cover the rate. Time, and again, this is right here, interesting. So it reads, on takeoff, right here, from the airport, it encounters a headwind and takes 34 minutes to reach a jump site. So again, you might be tempted to write a 34 right here, but don't, because we are putting this problem in terms of miles per hour. So we're going to have to also put my time in terms of hours. So 34 minutes is what fraction of an hour? Well, that would be 17/30ths, because 34 minutes is 30 over 60. You reduce that and you get 17/30ths. The return trip from the jump site takes 30 minutes. And again, well, that's pretty easy, right? 30 minutes, that's just 1/2. And we have our problem set up. And it looks like we would equate the two problems here to get my wind. And let's see, how far is the airport to the fire? Just a little bit of thought would get to that point. Example 11. I don't think this is too difficult, so we're going to go ahead and just snip the whole thing. I don't think there's too much I need to explain here. So MLA can travel 16 miles upriver in the same amount of time it takes her to travel 24 miles downriver. If the speed of the current is 4 miles per hour, how fast can her boat travel in still water? Okay, so we could see there's not necessarily a table here, but what we're doing is we're equating the time upriver is equal to a time downriver. And then from there, we'll figure out how fast her boat's traveling in the water. So if she travels 16 miles per hour upriver, the same amount of time it takes to travel 24 miles downriver, we see the equation that we'd set up. And let's see, okay, here it is. Using the formula distance equals rate times time, we can solve for t by obtaining t is equal to d over r. So how do we do that? So let's just look at this again. Distance is equal to rate times time. How do we get to this point? Well, that's easy. We solve just for t. And solving for t would be time is equal to distance over rate, which is right here. Okay, so this is a time problem, so therefore we're going to be solving for time. And that's exactly what this problem is doing, is solving for time. So we look at our time is distance divided by rate. So we would say, well, the distance, 16 miles, divided by the rate, which is r minus 4 with the going upriver. And then the distance here, 24 miles, right here, divided by the rate going downriver is r plus 4. So this, again, is just a manipulation of my distance equals rate times time, and that's really it. You solve, obviously, we multiply by the least common denominator on both sides and proceed from there. Now we're going to get to the main event. And I call it the main event because it is very interesting. And on top of that, I actually came across a YouTube video that is very similar to this problem. And it reads, actually, let's see. The title is, Most U.S. College Students Cannot Solve This Basic Math Problem. The Working Together Riddle. Right? We are going to not be a part of the most U.S. college students crowd, and we're going to learn how to do this. And I will also give you the link of the YouTube video in the announcement, so you can take a look. It's 7 minutes long, so you can take a look at it if you want to. For work problems involving multiple workers, such as people, copiers, pumps, etc., it is often helpful to consider the rate of work. And I think this whole thing needs to be snipped. And I will say, to further add on to the YouTube video saying most U.S. college students cannot solve this basic math problem. For those of you that are unaware, okay, so in order to get into undergraduate college, right, just your normal run-of-the-mill college, here in the South, I think we take ACTs. Other parts of the country take SATs, and you're given a score, or you're not given a score. You receive a score, and depending how well you do, you will get admitted or you will not. Excuse me. There's another test very similar to get into graduate school. So to get into school after college, and it's called the GRE, the Graduate Readiness Exam. It consists of a math portion, an English and reading portion, and then a writing portion, which I don't think anybody really gives a crap about. Well, the math portion, you will see these problems pop up on the math portion, at least 2 of them, all right? And if you can get this problem right, you're going to be in, good shape, because these are one of the harder type of problems. So let's break this down and see what it's saying real quick. Rate of work. The rate of work is the number of jobs that can be completed in a given unit of time. If one job can be completed in t units of time, then the rate of work is given by 1 over t. It's pretty easy. When dealing with 2 workers, use the following formula. And I promise you, this formula will do you good, especially if you plan to go to graduate school later on. And the formula is simply 1 over t sub 1, so it's going to be the work rate of the first worker. That's where the little sub there comes in. Plus t over 1 over t sub 2, and that's equal to 1 over the total time. Here, T1 and T2 are the individual times to complete one job, and T is the time to complete the job when working together. Okay, so let's get an example here. Just can fit it. We can't fit it there. We'll put it down here. Okay, so Brad and Michelle decide to paint the entire upstairs of their new house. Brad can do the job by himself in 8 hours. If it took them 3 hours to paint the upstairs together, how long would it have taken Michelle to paint by herself? Okay, so what I said was we're just going to use that formula. So real quick, we're just going to break this down. We're going to say Brad, we'll make Brad be B. And we're going to let Michelle be M. Okay. Now, obviously, this isn't the way we're going to break. We're not going to solve this way, but what we're going to do is just kind of think our way intuitively through this and then use our handy-dandy formula, and that handy-dandy formula is going to kill it. Okay. So anyways, Brad and Michelle, they're painting, so it takes Brad amount of time, it takes Michelle amount of time, and together, it's going to take them 3 hours. Okay. So how would I go about setting up this particular equation if I'm going to be following along with this? Okay. Well, what I'm going to do is I'm just going to let Brad be Brad, and it says that Brad can complete this by himself in 8 hours. So if Brad can complete this in 8 hours, following this formula, it looks like we're putting 1 over their total times. And that's literally it. We're just going to be putting 1 over their total time. So Brad can do it in 8 hours. Michelle, we don't know how long Michelle can do it in. Okay, Michelle does it in Michelle hours. She does whatever she wants. And they do it, they can complete the project in 3 hours. And that's it. I just set up my equation. That is 100% it. And of course, what we're going to do here is, and you know what, I'll go ahead and take the, let's see again. I keep forgetting. All right, so we have plenty of time. So I'm going to multiply by the least common denominator on both sides, which would be 24m. So if I multiply the left side by 24m, I'm going to get 3m plus 24, and that's equal to 8m. Okay, and if I solve for m, 24 fifths, and 24 fifths, okay, so we can't just leave it as 24 fifths, right? So if somebody asks you, hey, how long are you going to be here, or how long till you get here, and you say 24 fifths hours, they're going to hang up on you, right? So that would be 4.8 hours. Okay, but same process. If somebody says, you know, they'll be there in 0.8 hours, you know, you don't really like that. So we do 0.8 times 60, so that'd be 48. So it would be 4 hours and 48 minutes. So Michelle can finish painting by herself in 4 hours and 48 minutes. And that's it. This type of problem, the rate of work problem, I know you've seen them. Flashbacks to your ACT, you know, maybe your college algebra course in high school, or whatever, your algebra 2 course in high school, and you might have forgotten this method, but this is very easy to do. There is a second method, and I wouldn't necessarily is my preferred, but it is something I want to go over. And there's method 1. It is something that I'm going to go over because the YouTube video I'm going to send you about the college students that can't solve the problem, this is how they solve the problem. Method 2. And another method is based on the fact that time working on a job times rate to complete the job is equal to the fraction of job completed. Okay, so the fraction here, or the thought process again here is, and again I did break it down there, but time working on a job times the rate to complete the job is equal to the fraction to complete the job. So what is this over here? Well, the fraction to complete the job, that fraction is a 1. That means 100%. That means we have done 100% of the job. And if it takes 3 hours to complete the entire job, we look at the fractions of both Michelle and Brad, I think was the name. Yeah, there it is, Brad and Michelle, sorry. Then we still get the same solution. T is equal to 24 fifths. Now, this isn't what I'm going to necessarily teach us on because it's not, I honestly prefer the other method, but the YouTube video that I will send out concerning this related that's not related work problems. What the heck do we call them? Rate of work problems. This is how they solve it. And I think it's very interesting, and you are now not going to be part of that 90% of the U.S. college students cannot solve this problem. Anyways, that concludes the lecture.